Hello everyone, welcome to the Luminous Science, and today we are going to discuss about the topic aromaticity and basicity of pyrrole and pyridine. As we know, both pyrrole and pyridine are heterocyclic compound, and we have also seen their property and the proof for their aromaticity in our previous video. Now let us see the exact proof for the aromaticity and basicity of pyrrole and pyridine. Now first let us see for the pyrrole. So pyrrole is a resonance hybrid of the following canonical form. Ion or lone pair of electron or nitrogen are involved in the resonance. So we know that this is the structure of pyrrole, and we can see here there are one lone pair of electrons on the nitrogen atom. So the resonance in the pyrrole ring or resonance in the pyrrole is mainly because of these lone pairs of electron which are present on the nitrogen atom. So here we can see the resonance structure of the pyrrole. As mentioned earlier, the resonance structure of pyrrole is mainly because of the lone pair of electron. Due to the resonance of lone pair of electron, the stability of the compound also increases. And to prove the aromaticity of pyrrole, here we'll consider there are two double bond which gives us 4 pi electrons, and also here we have one lone pair of electrons. So the total number of electrons which are involved in the conjugation or in the double bond or also for a resonance structure is 6. Now when we are applying n is equal to 1 and for the Huckel rule, that is 4n plus 2 pi electrons. So when we put n is equal to 1, then 4 into 1 plus 2, which gives us 6 pi electron. So if there is presence of 6 pi electrons and obeying the Huckel rule of 4n plus 2 rule, then we can say that the given compound is aromatic in nature, which is seen in the pyrrole. Now let us see the explanation regarding this. So the pyrrole, it has 4n plus 2 pi electron, where the Cn bond is 1.38 Armstrong, which is shorter than the normal Cn bond, which is of 1.48 Armstrong. Thus, which indicates that Cn bond has significantly a double bond character. And the shorter bond angle between the Cn bond in a pyrrole ring is mainly because of the presence of lone pair of electrons on the nitrogen atom. Since carbon is an electrophile in nature, the lone pair of electron which is present on the nitrogen atom will tend to move towards the carbon atom which is present adjacent to the nitrogen. And so due to the electron-electron pull, the bond distance between the carbon and nitrogen will be shorter. And due to this shorter bond length, we can see there be a arise of partial double bond character between the C and N bond. Then aromaticity of pyrrole is explained in terms of hybridization. In pyrrole, all the 4 carbon atoms and nitrogen atom will undergo sp2 hybridization, which we will discuss now. Then sp2 hybrid orbitals of carbon and nitrogen atoms overlap with themselves with the s orbital of hydrogen atom to form a carbon-carbon, carbon-nitrogen, carbon-hydrogen and nitrogen-hydrogen sigma bond. Sigma bond is nothing but single bonds. Now let us see the hybridization, and which is also called as energy level diagram of carbon and nitrogen atom. Now when we consider the energy level, we can see there is a ground state and also the excited state. We know the electronic configuration of carbon is 1s2, 2s2 and 2p2. Now if we see in the ground state, there are 2 electrons in 2s orbital and 2 electrons in the 2p orbital. Since we are only considering the valence orbital, that is 2s2 and 2p2. And once the atom get excited, we can see there is 1 electron in 2s orbital and 3 electrons in the 2p orbital. Once these valence electron undergo hybridization of sp2, so here it is s orbital and here it is p orbital, and here we can see the hybridization of sp2 orbitals, which we call them as sp2 hybrid orbital, and one of the p orbital will remain unhybridized. And similarly, in case of nitrogen also, we know the electronic configuration of nitrogen, that is 1s2, 2s2 and 2p3. Here also we'll consider only the valence shell electron, that is 2s2 and 2p3. Here also in ground state, we can see there are 2 electrons in 2s orbital and 3 electrons in the 2p orbital. Once the atom get excited, the electrons will also jump from ground state to excited state. That is, 1 electron from 2s orbital will jump into the 2p orbital, and which leads to the formation of sp2 hybridization. Here there is a p orbital which is unhybridized, having a pair of electron. And here we can see 1s orbital and 2p orbital will undergo hybridization, leading to the formation of sp2 hybrid orbital. Now let's see the explanation behind the excitation. They lie in the same place. Each carbon is left with one unhybridized p orbital containing 1 electron, whereas in case of nitrogen atom is left with one unhybridized p orbital containing 2 electrons. So, these p orbitals overlap sideways to form a delocalized pi electron cloud encompassing all the 6 electrons. Thus, it contains 4n plus 2 pi electron and it is aromatic in nature. So, the aromaticity behind the pyrrole molecule is because of the p electron, unhybridized p electrons, which is present and compassing 6 electron and which will help in obeying the Huckel rule, that is of 4n plus 2 pi electron. And we know that pyrrole is basic in nature due to the presence of lone pair of electrons on the nitrogen. It reacts with dilute hydrochloric acid to give a crystalline HCl salt, but it is a weak base. We know that pyrrole is a base, but when it undergoes a reaction with a dilute HCl, it leads to the formation of a crystalline HCl salt. Comparatively, the salt form will be weaker base when compared to the parent molecule, that is of pyrrole. So here is a general reaction representing how when pyrrole reacts with a dilute hydrochloric acid give rise to a formation of a crystalline hydrochloric acid salt, and which is weaker when compared to the pyrrole in case of basicity. Now, if we see the reason behind the weak base character, the reason for weak base character is that the lone pair of electron on the nitrogen, it reacts with the dilute HCl to give a crystalline hydrochloride which is involved in the delocalization and not easily available for donation. Also, when the proton is added, it loses its aromaticity character and becomes less stable. As we already know that the lone pair of electron which is present on the nitrogen atom is usually involved in the resonance, which leads to the stability of the molecule. When the dilute HCl is made to react with pyrrole, the lone pair of electron will not actively participate in the bond formation, or the donation of lone pair of electron on nitrogen atom will not be available when HCl is reacted to it, thus leading to a formation of a less stable and also a weaker base. And also when proton is added, the aromatic character is lost and it becomes less stable. Now we'll see the aromaticity and basicity of pyridine. And we also know pyridine is an heterocyclic compound and it is aromatic in nature, and the resonance hybrid of following 5 structure. We know that this is the structure of pyridine, and the 5 resonating structure of pyridine are as follows. And here also we can see that there is a lone pair of electron on the nitrogen atom. Here, the resonance energy is about 125.5 kilojoule per mole. Now, what does resonance energy mean? Resonance energy, which is also known as delocalization energy, is a measure of the extra stability a molecule gains from having a delocalized electron. Instead of being locked into a single Lewis structure with fixed single and double bond, some molecule distribute their pi electron across a multiple atom. This electron sharing lowers the molecule's overall potential energy, making it for more stable than any single structural drawing would suggest. So in simple words, we can also understand in this way that the lone pair of electrons which is present on any of the atom which is in a molecule or a compound will lead to delocalization of electron. Once there is delocalization of electron, the stability of the electron will also increase, thereby holding all the bonds tightly so they do not react so easily with any of the reagent which comes in contact with it. So, the extra stability which is given to a molecule in the presence of a lone pair of electron is nothing but resonance energy. And in pyridine, we can also see it. This will obey 4n plus 2 pi electrons. Here we can see there are 6 pi electrons which are involved in the bond, and similarly we have seen in pyrrole where that obeys 4n plus 2 rule, and here also pyridine will obey 4n plus 2 pi electron rule. And here also the aromaticity is also explained in terms of hybridization. All the 5 carbon atom and nitrogen atom will undergo sp2 hybridization, as seen similar to that of the presence of electrons in both the carbon and nitrogen atom in pyrrole. Here in pyridine also, when we consider a carbon atom whose electronic configuration is 1s2, 2s2, 2p2, here also at the ground state there are 2 electrons in s orbital and 2 electrons in p orbital. When excitation takes place, one of the electron from 2s orbital will jump into 2p orbital, which then undergoes a process of hybridization, that is of sp2 hybridization, leading to a formation of sp2 hybrid orbital, and one of the p orbital will remain unhybridized. And now the sp hybrid orbitals of carbon and nitrogen atom will overlap with themselves and with s orbitals of hydrogen atom to form carbon-carbon, carbon-nitrogen sigma bond. They lie in the same plane. Now each carbon is left with one unhybridized p orbital containing one electron, which is seen here. There is one p orbital which is not involved in the hybridization, bearing only one electron. And also since we have seen in pyrrole, there is in case of nitrogen, the nitrogen atom also left with one unhybridized p orbital containing only one electron. These p orbitals will overlap sideways to form a delocalized pi electron cloud overlapping all the 6 electrons, and thus it contains 6 electrons, which is nothing but 4n plus 2 pi electrons, and also proves it is aromatic in nature. And one sp2 hybrid orbital of nitrogen contains a lone pair of electrons. And by the presence of lone pair of electron on the nitrogen atom in the pyridine structure, we can say pyridine is basic in nature, and when it reacts with acid, it gives a fairly stable salt. Unlike the lone pair of electrons of nitrogen in pyrrole, the electrons of nitrogen in pyridine are not entirely involved in resonance, but they also actively participate in any kind of reactions. The general reaction is represented here. We can see the explanation here. The lone pair of electrons of nitrogen is not involved in delocalization, so thus it can readily donate this pair of electron, and thus it is basic in nature, and it is also stronger than pyrrole. In pyrrole, the lone pair of electron is involved in the delocalization and not readily available for donation. But whereas in pyridine, it is not involved in delocalization and can be readily donatable. And therefore, pyridine is stronger base when compared to pyrrole. And also, but it is weaker base than trimethylamine. In trimethylamine, lone pair of electrons on nitrogen is present in sp3 hybrid orbital, which has a 25% of s character. And whereas in pyridine, it is present in sp2 hybrid orbital, which has 33% of s character. Therefore, in pyridine, the lone pair of electron closer to nitrogen nucleus than in the trimethylamine, and thus trimethylamine is stronger than the pyridine. And here we can see the structure of trimethylamine, where the 3 methyl groups are attached to a nitrogen atom, and this nitrogen atom is bearing a lone pair of electron. So in this video, we had seen about the aromaticity and basicity of pyrrole and pyridine. If you have liked this video, kindly subscribe to the Luminous Science, like and share. Thank you for watching. See you all in my next video.